equation that we derived from the previous video. And so we're going to use this equation to make our simulation. Alright, so keep in mind that this equation here, it only refers to a1x, but we could basically use this equation for a1y, a1z, a2x, a2y, a2z, a3x, a3y, and a3z. It's going to be basically in the same format, but what we're going to have to do is change the values for m2, m3, the radius, and these coordinates as according to what it's referring to. You'll get what I'm saying now when I start that part of the code. But first of all, what we're going to do is assign these values. So we're going to need our mass. So I need that, and I'm just going to say that I'm going to give it a value of 100 because for now I'm just going to give it a value of 100. I'm just going to first of all save that into a 3D pre-objects gravitational interaction simulation. Yeah, I'm going to call it like that. And for now, I'm just going to give all three masses a mass of 100 units. And now, what we're going to need is, you see, notice that the radius here, we're going to have to refer to this radius. Alright, so this radius here is a vector quantity, is a vector radian. It's kind of like the displacement. And so, if something is going from P1 to P, the radius from P1 to P2 is going to be different to the radius from P2 to P1 because they're in the opposite direction. So the radius of P1, P2, if I'd say that is a positive value, radius of P2, P1 may be a negative value. And so we're going to have to create a total of 6 radiuses. That's going to go like, let's say R from 1 to 2, I'm going to say it like that. We're also going to need R2 to 1. We need R1 to 3, and again, need R3 to 1. We're also going to need R2 to 3 and 3 to 1. 3 to 2. Yeah. And then what we're also going to need is the positions. So the position quantities that our acceleration is going to define. Well, our acceleration and our velocities are going to define our positions, but we do, of course, need our position coordinates. And so we need the x-coordinate of P1, we need the y-coordinate of P1, we need the z-coordinate of P1. And I'm just going to copy these 3 times, and these 3 should be about coordinate 2, and the last 3 should be about coordinate 3. Okay, and what else do we need? Well, first of all, I'm going to assign some values. And yeah, one thing I want to mention is that imagine we're going to have a 3-dimensional, we're going to have x, y, and the z plane. And so I want one of the objects to be only have an x coordinate. So one of the objects, they're going to have both y and z coordinate of 0. And one of them would have an x and z coordinate of 0, and one of them would have an x and y coordinate of 0. And so that when we do that, we could, it's going to be an easy way to define our positions. But what I also want to do is give those x quantities of P, so the x coordinate of P1, y coordinate of P2, and then z coordinate of P3, I want to make them random so that every time I run the simulation, it's going to be a different picture. And so here I'm going to say a random point between, say, 150 and 200. And I said before, these 2 would be 0. And for P2, our y coordinate would be assigned a value, so random of 150 and 200 again. And the x and z is going to be given a coordinate of 0. And the same here, x and y will be assigned 0, and its z coordinate would be given a random coordinate, a random coordinate. And what we also have is the velocity, so float v1x, and we want the initial velocity to be 0, We also want v1y. We also want the velocity of v1 of object 1 in the z coordinate, so v1z. And again, we're gonna copy this 3 times. And here, of course, we need v2 and v3. All right. Now what we're gonna need is the acceleration values, and these acceleration values are going to be defined by this equation, but for now I'm just going to give them a value of 0. I'm just going to assign them, I'm just going to declare them, yeah. a1x, a1y, and a1z, again. And we do the same thing, we multiply this by 3 times because we have 3 objects. Alright, and then what we need is, we're going to need some value. Notice in the code that I'm going to draw the trail that the object goes through, and it's similar to what I've done in the previous videos in the double pendulum simulation and the elastic collision simulation. Well, what I did was to draw the trails of that object, I needed to record. I needed a record of the previous values of the positions, and so that when I draw a line between the previous value, the previous position, and the current position, I get a line, and those lines, when they added up, they seem like a curve, and that curve tells us how the object is the trajectory, the object is moving. And so I'm going to do the same thing here. I'm going to need the previous value for p1x, and for now I'm just going to declare it. Previous value for p1y and previous value for p1z, and do the same thing for p2 and p3. So again, multiply 3 times p2 and p3. Alright, then I say, now I'm just gonna do the same things I always done. So pgraphics canvas. I'm going to set up my canvas, and I noticed that the biggest screen I could get is when I get the size as 1500 and 900, and set the frame rate as 0, frame rate as 60, I'm sorry, and canvas. Make our canvas too. Set the color of our canvas background, and that's basically the setup is now complete. And now all we have to do is begin our algorithm. So we have our draw function, we have our image. We're going to need so first of all, I'm just going to set my color as completely dark, so stroke 0, and then give a stroke weight of 2. And what I'm going to draw now is the actual objects that are moving. And then I would also have to declare the ball size, the sizes of the balls, and the size of the lines. That's going to be important to give the illusion that our simulation is actually on a 3D plane, although it's basically, our screen is 2-dimensional, but to give the illusion that it's a 3-dimensional environment, I'm going to set the line size and ball size to change, so that when it's closer, so when these z value of the object is bigger, the line size of the trajectory and the ball size will increase, to give that 3-dimensional feeling, or I'd say illusion. Right, so now what I'm going to do is I'm going to get, I need ball size 1, I'm going to set that, as I said before, the bigger the value for P1Z is, the bigger the ball should be. So I say about 10 plus P1Z divided by 10, if I do that. And also we would need a limit to the ball size, because when the ball size becomes a negative number, we see that an error occurs in the code. So I'm going to need a barrier. I'm going to need the maximum ball size, and I'm going to set that as about 1. So when ball size is smaller than 1, I'm just going to set it as the stop at 1. So it's just going to give a value of 1. And it should be ball size 1. And repeat the same thing for ball sizes 2 and ball size 3. So ball size 2, again, we have P2Z divided by 10, ball size 2 smaller than 1, ball size 2 equals 1, ball size 3 is 10 plus P3Z, if ball size 3 is smaller than 1, give a value of 1, simple. And now what we're going to do is actually draw the circles, the objects. I'm going to start with ball 1, and I'm going to set the color of ball 1, and that's going to be 00FF00, which is basically using the RGB scale, it's green. So our first ball is going to be green, and I'm going to basically draw a circle. And now, in defining the coordinates of a 3-dimensional object in a 2-dimension, we said in the previous video that we're going to subtract the z-coordinate divided by the square root of 2 from both the x and y coordinate to give the sense that the z-coordinate is actually accounting to a change in the 2-dimensional environment. So that's going to be P1z. Our x-coordinate of ball 1 is going to be P1x minus P1z divided by square root of 2. And now here, because in processing we refer to the positive x-coordinate as right, so this is the same, but we refer to the positive y-coordinate to down, so it's going to be all opposite. So the whatever value we want in the y-coordinate, that should be opposite. So here we're going to need minus P1y plus P1z divided by square root of 2. Opposite to C, here we did plus and minus, here we need minus and plus, because the y-coordinate down is positive in our processing environment for whatever reason they decide to do. And as I said before, I'm going to need, so the radius of our ellipse, our circle, would be our diameter is going to be P size 1, B size 1, the ball size 1, so both same as B size 1. So that's going to generate a circle that has a diameter of B size 1. And we do the same thing for, we do the same thing for our second ball and our third ball. But our second ball, so ball 2, that's going to be red, so FF0000. And our third ball is going to be blue, so 0000FF. And all I'm going to do is replace all of these by 2, so P1Y, P2Z, and ball size 2, and ball size 2. Same thing here, we replace everything by P3. Alright, and now what we need is define our radiuses. So the radiuses we have to define would be, first of all, we're going to have to define the radius from 1 to 2, and that's going to be basically the square root of the power, the power of, so there's going to be three powers that are going to be added, and it's going to be it's basically going to be the power of, so it's from 1 to 2, so it's going to be p1x minus p2x, and then p1y minus p2y, and p1z minus p2z. That's going to be our radius. And our radius from 3 to 1, so 1 to 3. So here what we're going to do is we're going to get an expression for a1 of x. And in a1 of x, you see that we need the radius from 1 to 2 and the radius from 1 to 3. And our radius from 1 to 3 is going to be the square root of the power, again, some power plus some power plus some power. And that first power is going to be p1x minus now p3x. Here it's going to be p1y minus p3y. And here it's going to be p1z minus p3z. And I forgot to, we're going to need comma 2 in all of the powers because, we need some value that we're squaring these values for. So we're squaring p1z minus p2z by a power of 2. So we're going to need 2's all here. And now that our radius is defined, we could get our expressions for a1x. And a1x, using this equation here, and notice that I'm not going to use the value of g here, because by adding the value of g, it makes the simulation so slow. And all we want to see is how the interactions look like, not how it would really look like in real life. And so to make the simulation faster, I'm just gonna not use the value of g. Alright, so that's gonna give us minus of some big bracket, and that big bracket is constructed by two smaller brackets, so two smaller fractions. And our first fraction is going to be m2 times some fraction again, divided by the power, some power. And here also we're going to need m3 times some bracket divided by some power. Now, inside the first bracket, we're going to need x1 minus x2. So p1x minus p2 of x, and divided by the power of r from 1 to 2 cubed. And here we're going to need p1 of x minus p3 of x, and the power is going to be the radius of 1 to 3, and our power is going to be 3. Now, we could do the same thing for, as I said before, a1y and a1z. It's just simply calling them y and z, and replacing everything here by y values. So p1y, p2y, p1y, p3y, and here basically p1z, p2z, p1z, p3z. And that's it. That we have just defined our a1, x, y, and z. It says a1, z does not exist. Here. That was just a mistake, yeah. And now we could do basically the same thing. But to make the process faster, I just realized that the radiuses, they're just going to be same. So yeah, that was my mistake. The radius is, so from r1 to 2 and r2 to 1 are going to be same. There's not going to be any negative sign or positive sign. They're just going to be positive signs. So let's just say, so for a2, the acceleration values for a2, we're going to need, what we're going to need is from 2 to 1 and from 2 to 3, because they're relative to 2. And for 2 to 1, let's just say that's equal to, 1 to 2. And 2 to 3, we would have to define, our a new one because we haven't defined any radius between R2 between P2 and P3, and that's going to be it. I'm just going to copy this because it's going to be similar. That's going to be the power of P2x minus P3x, P2y minus P3y, and P2z minus P3z. And again, our A2x values then would be, it's going to look the same as this one here, but only difference being, so in this case we multiplied P2 from P1 and P3 from P1. So now we're going to have to subtract P1 from P2, so P2x minus P1x, and P2x minus P3x, because here we are doing everything in relative to 1, so we have 1 minus 2, 1 minus 3, and now we're going to have everything relative to 2, so we have 2 minus 1 and 2 minus 3. These values, they are going to be same, except for that here we're going to use P3 cubed. And everything else looks fine. Just going to have to swap that around. And is it right? 2 to 1, 1 to 2, 2 to 3. Yeah, here I'm just going to have to use P2 to 1, but it really doesn't matter because they're basically the same values. And yeah, that looks correct to me, so I'm just going to do the same thing for A2y and A2z. And the only thing changes here is the y, putting y here and z here. Y here also, and z here, and also a z here. Alright, and now what's left is doing the same thing for A3, and so we're going to need the radius from 3 to 1 and the radius from 3 to 2. And these are now easy because we can say that's equal to radius of 1 to 3, and that's equal to radius of 2 to 3, which we have already defined. And so A3x, using the one from here, that's going to be from 3 minus 1, from 3, and from 3 minus 2, and we're talking about M1 here, interaction between M1 here, so we're going to need M1, and radius from 3 to 1. Here we're going to need a mass of 2, P3 minus P2, and radius of P3 to P2, R3 to 2, but it really doesn't matter. But I'm just going to do it for the sake of it. And yeah, that looks right to me. 3 minus 1, 3 minus 1, 3, 2, 1, 3 minus 2 and 2. And so we're gonna need to basically do the same thing, y and z. And the y is here, and the z value is here. Alright, that looks about right. And so what we're going to have to do is now it's simple. We have v1 of x, and we know that that's going to be, we're going to have to every iteration of our draw function, I want the acceleration value to be added to the velocity value, and then in every iteration I want the velocity value to be added to the position value. And that's basically it. So and so I'm going to have to multiply all of that 2 times and get the same thing for v1y and p1y, v1z, a1z, p1z, v1z. And all of that I'm going to have to do the same thing, but change every value to in terms of V2, A2, and P2, and here about the values for object 3. Okay, and now it's basically it. I'm just gonna do, now we have to draw our canvas, so canvas.begin draw. I say, first of all, we need the translate function as we did before. Because the canvas starts here, we need it to go to the center. And first of all, I'm just going to draw the axis. So we need the x-axis, y-axis, and the z-axis. So set a stroke weight of, let's say, 1, and give a color of black, so that. And we want a line that goes from the center here to all the way here, because it is the x-axis. So we need from 0.0 to 1000, 0. And what I also want to draw is a dotted line that goes to the negative x values. So for that, I'm just gonna have to do. I'm gonna need a for function. So I'm going to need a loop that draws the dash lines. I'm going to need about 50 iterations, and say that, well, we need, I'm going to, the color, so we need a blank space and a drawn face. So black line, no line, black line, no line, black line, no line, and so on. So if I say I'm going to draw the blank line first, so this is white, so it's not going to be seen in the canvas, and I'm going to need to draw a line from -20 times 1 times I, comma 1, comma 0, -20 times I, -10, so going 10 more from that point, comma 0. And basically now we assign it to a black line, so a visible line, and from -20 times I, -10, comma 0. From there I'm going to go to -20, comma I, -20, comma 0. And that would hopefully draw our line. And for some reason there's an error here, so -20, comma I, comma 0. Yeah, there's going to be a comma here. Yeah. Alright, so that would hopefully draw our x-axis. And basically what we do is repeat the same thing for drawing our y-axis and our z-axis. So, but the z-axis is going to be slightly different. So for now, let's see how it goes. We have, from now we're going to draw a line from 0, 0 to this point here, which is 0, -1000. As I said before, the y coordinate is flipped. And so we're going to do the same thing, but now what we're going to do is say it's going to remain at a coordinate of 0, so x coordinate of 0, so 0, 20 times I times 0, comma 0, to a coordinate of 0, 20 times I plus 10. Yep. And that would ensure that these are all positive values, so it's going to go down. It's going to draw a dotted line down. That's what we want to do. So we have our blank space like that. So we need our visible line that goes from 0, 20 times I plus 10. That's our previous coordinate. To 0, 20 times I plus 20. Yeah, that would give a 10, 10, 10, 10, 10, 10, visible, non-visible, visible, non-visible, and so on. And now, this part is the quite complicated part. That's going to be our z line, z axis, I should say. And so first of all, I should say, I'm going to give a color, a slightly lighter color, so that if it's black, it's going to be 2. I see the z axis I think should be distinguished from the x-axis and the y-axis, so I'm going to give it a different color, a gray color, 8, 8, 8, 8, 8, 8. That's like, a gray color that is, kind of like the middle gray color. And our line should be from 0, 0 to minus some big value divided by square root of 2, comma, plus some big value divided by square root of 2. And so it's going to be something like from 0, 0 to somewhere over here, like that. And so the negative line should be a dotted line that goes from center to the first quadrant. And in order to draw that, we're going to need to say that, well, first of all, we're going to start at 20, I, 20, I divided by square root of 2, comma, minus of 20, I divided by square root of 2. And from that point to, we need a plus 10. We always said we need a 10 length dotted line and so 10 space, 10 lengths visible line, 10 lengths non-visible line. So we're going to need 20 times I plus 10 divided by square root of 2. And then we're going to need minus 20 times I plus 10 divided by the square root of 2. Yeah, that seems correct. And now what we're going to need is, again, a gray color. And from the previous coordinate, so this coordinate here, we're going to start there and then draw 20 times I, now not plus 10 now, plus 20 because we have moved 10 coordinates more in the x direction. And then, of course, square root of 2, comma, minus, again, 20 times I plus 10, plus 20 divided by square root of 2. That would give us our dotted lines. Let's just see if that is working. Yeah, there's a typo here. Okay. Wait, let's just finish doing and then see if it works or not. Right, so now we need our size of the line. So you see that the trajectory our objects take, I want them to be, I'd say, I want them to be, yeah, I want the thickness of the lines to be bigger as the objects become larger, because logically that makes sense, because the larger the object becomes, the marks that they leave would be bigger. And so I want L size of 1 to be similar to ball size here, but now it's going to increase in a smaller magnitude, so about divided by 100. And then if L size is smaller than 0.05, that's going to be our limit, so I'm going to get that equal to just 0.05. And yeah, L size 1, of course. Yep, and then we do the same thing for L size 2 and L size 3. So L size 2 is 1 plus L2z, and L size 3 is 1 plus L3z, and the same thing. Now all we have to do is draw those lines. So I'm going to set the stroke weight as L size of 1. And again, it's object 1, so we need green. So 0, 0, FF, 0, 0. And then I'm going to say if the frame count, only if the frame count is 1. So after the first iteration of our loop, our draw loop, only then we're going to say that canvas dot line is going to be equal to the line from the previous coordinate to the current coordinate. So that's going to be previous p1x minus previous p1z divided by square root of 2. That's going to be our x coordinate, comma, minus p1y plus p1z divided by square root of 2, comma, just p1x minus p1z divided by square root of 2, comma, minus p1y plus p1z divided by square root of 2. Yeah, and then I'm going to also draw a point so that there's no confusion. So I'm going to draw a canvas point, and say p1, that's going to be our current point, so p1x minus p1z divided by square root of 2, comma, minus p1y plus p1z divided by square root of 2. And then now I'm just gonna set my stroke as invisible to not make any confusions between moving on from this line to that line to a different line. And now I'm just gonna copy all that and do the same thing for object 2 and object 3. So here I'm going to say L size is 2, and we know that our color for object 2 is red, so FF0000. And all we have to do is change all of that to P from P1 to P2. So previous P2, previous P2, 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 and P2, P2, and P2, and P2, and P2. Yeah. And for L size 3, we know that that's going to be RGB, so blue. And all of them would be given a value of 3. So we're dealing with the coordinates in the coordinates of object 3, and we do the same thing here. Yeah, that looks about right. And now we're just going to say, well, end draw. But we still haven't defined what our previous values of these coordinates are. So we're just going to say, well, P of P1x is P1x. But after this loop is done, the loop is going to start all over from the start. And as we go down, the values that the code uses for P1x would be just P1x, but from the loop prior to the current loop, because we have this, we assign this value after we use it. And so after the first iteration, this is declared, and then that goes back to the top. We follow that down, and this value is going to be this value from the previous loop, but this value is going to be P1x from above, so the new value. And so that would create our, that logically makes sense. So we do the same thing with P1y and P1z equals P1z. And all we have to do now is do the same thing for previous P2, 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 and P3, 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 and P3. Yeah, I think that's done. And yeah, let's see if the code works. Let's see if the animation works. So we have our animation here. yeah, they're getting closer together, and then yeah, they're basically working. But we see that because we didn't declare a maximum value for acceleration, we see that they just sometimes, a lot of the times, they will just hit each other, and then they're just so close before they hit, and then they just, yeah, they kind of explode out. But I don't really want that. So I would set a maximum acceleration value in all of them. So if the acceleration value is bigger than some value, just just limit it from becoming that value. So I'm just gonna do that really quickly. So I'm gonna say that after we assign these values for, assign our acceleration values, what I'm gonna say is, now if a1x is bigger than something like 0.4, I'm gonna say, well, then just set it as 0.4. So don't let it surpass the value of 0.4. But we also know that it's a vector quantity, so we're gonna need, so what if it's smaller than minus 0.4? Well, then we do the same thing. Well, we say that a1x now is equal to minus 0.4. And yeah, we're just gonna have to do that for all of our values. So that was a1x, so we need a1y. Same thing for a1y, and the same thing for a1z here. a1x, a1x, a1y, a1y, I'm sorry, a1y, and a1z. So if one of those acceleration values in any dimension exceeds some value, we're just going to say, well, then just make it into this value. And of course, we're going to have to do that for everything. So we're going to need a2, 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 and a2. And basically do the same thing for a3. And that would be, I hope that would be done. We're not going to see some crazy explosions, but see a stable and less radical less radical animation. Let's see. So they're going, and then they're not exploding, but you see that they're curving back towards them. And you see the green ball here is kinda did explode, but these two are still interacting with each other. You could see. Yeah, it's really cool, right? You get these random motions, but I wanna keep running until we have something like I want a setting where the three objects continually do with them each other. But yeah, I'm gonna find that situation, and then I'm gonna share that with you. But for now, I think this video is until here. If you go to the link in the descriptions below or the comment section, I'm gonna post a link to the text file that has all of this code. So if you want to use that code to try it yourself in processing, you could do that too. And yeah, thank you for watching. It was Joe Stemcorder in the physics session, making a three-dimensional, three-object gravitational interaction simulation. Thank you, and as always, please like and subscribe, and yeah, see you in the next video.